basic depth-first search, every step costs exactly the same. But in the real world, paths carry specific weights, factors like distance in miles, time in traffic, or network latency. This chart situates our solution to that weighted routing problem right in the center of the computer science landscape. Algorithm number 15, Dijkstra's algorithm. How do modern navigation systems calculate the absolute cheapest route across a map containing millions of nodes and do it in milliseconds? Dijkstra conceived the solution to this massive digital routing problem entirely in his own head, without using a single physical tool. In 1956, a young programmer named Dijkstra was sitting with his fiancée on a cafe terrace in Amsterdam. He was mentally chewing on a demonstration problem for the ARMAC, a massive early computer. He needed to find the absolute shortest travel path between 64 different Dutch cities. Because he was shopping and didn't have a pen or paper with him, Dijkstra couldn't rely on brute force calculations. He had to design a rule that avoided all avoidable complexities. He realized that if he kept the logic simple, he could process the entire map flawlessly, committing to one path at a time without ever having to second-guess a previous step. That realization became the algorithm's golden rule. Greedily finalize the closest unsettled node, then relax its outgoing edges. This diagram illustrates exactly how that plays out. We establish a starting board state by setting our source node's distance to 0 and treating the distance to every other node as infinity. We make our first move by settling the origin node, A. From A, we evaluate its immediate neighbors, pulling B's tentative distance down to 4 and C's distance down to 1. Now the greedy logic takes over. C is our new closest unsettled node at 1, so we lock it in. From C, we find a cheaper detour to B. B's distance drops from 4 to 3. We repeat this process, settling the remaining nodes in order of their lowest current cost. The result is a completed shortest path tree, where the indirect route from A to C to B actually beats the direct connection. This one-way commitment works because we assume all weights are positive. Any extra edge added to a route later will mathematically only add cost, never subtract it. This graphic displays the mechanical engine keeping the algorithm from endlessly scanning, a min priority queue, usually structured as a binary heap. It continuously hands back the closest unsettled node. On the left, we see the Python logic for relaxation. Distances only ever move down. If going through a new node offers a lower total cost, we overwrite the old path and push the new distance back into the heap. This table breaks down the time complexity payoff of that choice. Popping nodes and relaxing edges via a binary heap yields near-linear execution speeds, even on incredibly sparse graphs. Marrying that elegant one-way logic with a highly structured priority queue turns a clever thought experiment into an industrial-scale routing engine. Today, every time your GPS app calculates the optimal drive time through a sprawling city grid, it is running this exact logic. Behind the scenes, internet routing protocols like OSPF and ISIS use it to map link-state networks, and autonomous robots rely on it for physical pathfinding. This 20-minute thought experiment, designed to avoid complexity, now provides the core logic for nearly every GPS device and internet router on the planet. But this diagram exposes the algorithm's single, load-bearing vulnerability. It completely collapses if an edge has a negative weight. A negative edge acts as a hidden discount. It tricks Dijkstra's greedy rule into locking a node too early, entirely missing a cheaper detour that appears deeper in the network. To account for negative costs and detect negative cycles, we have to abandon the speed of the greedy settle. We need an algorithm willing to reevaluate every path multiple times. We need Bellman-Ford. You can trace that exact algorithmic evolution and 49 other foundational concepts in the book 50 Algorithms Every Programmer Should Know.